Assalamualaikum, my name is Anis Arina Syazwani Borhan.
My name is Aida Nadira binti Mohamad Noor.
My name is Fateh bin Zailan.
My name is Wana Sabrina binti Wan Haziruddin.
My name is Hakim Zikri bin Asirin.
And we are from Group 1. We use this 3-bus system which consists of slack bus, generator bus and load bus. We chose MATLAB as our software to simulate the system in steady state, in fault and after application of suitable protection.
Okay, hello. Today I will show you how to simulate our power flow. First of all, I'm used this power flow from the Hadisha art book, Power System Analysis, figure 6.12, page 217, which is in the power flow have 3 buses. Bus 1 is slack bus, 3 bus 3 is generator bus, and bus 2 is load bus. Okay, first we will open the MATLAB and then press the icon Simulink here, and then you choose the blank model. Okay, and then you choose the library browser. You press the library browser, and then this Simulink library browser will appear. Then you make it spread so you can see. First of all, we will type the power guide. So I already type power guide. This is for analysis our load flow. We can drag it, or we can right click and add block to the model, or you press Ctrl I. You can choose 3 options lah to drag this block diagram. Okay, then you go to you tap 3 for 3 phase, then you search for our source. Okay, we use the source, then I press Ctrl I. It will appear in this Simulink, and then press RLC to press enter 2 times. For you choose the 3-phase series RLC branch for our transmission line impedance, and then you press the load is for our load bus. Okay, you use the parallel RLC load, press Ctrl I. Okay, also we will take the load flow bus for our load flow analysis. And then don't forget, we also have to measure our power flow. You go to the okay, this 3-phase PI measurement. This is for measure our voltage and current. Okay, then I think already enough, so you can close and make it big. So now you refer from this Hadisha book. Okay, now for the 3-phase source, we have 2 source. What we're gonna do is just you press Ctrl C and press to the block and drag it out, so it will make a new copy. Also the 3-phase series RLC branch, press Ctrl C and drag it. Okay, for the also same for measurement, Ctrl C and drag. So this block will measure for 3 bus. Okay, now arrange it properly. Okay, now phase A, we connect to A measurement, and then this will appear the line blue, so you just click it so that automatically will connect to the another block. we arrange it just like the reference. Okay, this how you want to do is you just press Ctrl C to rotate it, so it will make easier to connect. Just arrange it to look beautiful. So this you can just drag it and see the beautiful. Okay, now arrange this for okay this okay this also you will rotate to how you will use it. A for A, B for B, and C for C, and then you rotate this generator, and then I also forget to display. This is display used for show our value measurement view. Okay, also same Ctrl C and drag it out. We will measure two things, voltage and current, and just connect it for measurement device. Okay, this also must put at the 3 bus so we can analyze the load flow. Just connect it to the every bus. You can see here the bus 1, bus 1, bus 1. Okay, right now we will setting the parameter for the select bus. The parameter have source, impedance. So for the face-to-face VRMS, we use the 11 kV. 11 kV. So E means power of 3. So 11 kV. So frequency we use 50. In Malaysia we usually use 50. So you use 50. So base voltage we face-to-face also 11 kV. So for the load flow generator type, we have 3 type: swing, PV, PQ. So we use swing as the slack. Press OK. Okay, setting for the generator bus next. Okay, also same face to face 11 kV, frequency 50. This we will make 0, 0, 11 kV. Okay, for the load generator type, we use PV. Okay, for the action power generation, we can refer to the reference. They use 200 megawatt and voltage 1.05. I forgot to put the select bus parameter voltage 1.05. The angle is 0, so we will arrange back. Okay, for this 200. Okay, just type 200. E6 means 200 megawatt. So this is infinity minus and infinity. So check back. It's alright. Right now we correct it. So here we multiply here 1.05. So the angle is 0. Here we will multiply by 1.04. Okay. Okay, then for the load, first the configuration with grounding. Nominal phase, the phase is 11 A3. frequency 50. For the active power, we see the difference 400 megawatt and 250 MVAR. So we correct it. This is 100 is 6 and this 25 is 6. Active power 400 megawatt and the reactive power is the 250 megawatt. So the capacitive is no, so we change to 0. And load flow, load type is we use the PQ because in the reference they give the data of PQ. So press OK. Okay, for the parameter in the three-phase series RLC branch means for transmission line impedance. Okay, for the branch type we use the RL. Okay, for the resistor we can refer here 0.02 J 0.04 0.0125 plus 0. Okay, just change it 0.02 here 0.04 slash open bracket 2 multiply by pi multiply by 50. Okay, for this means is for value J because here in that turn you see here is a Henry, so we change to in the J per ohm. So press OK. All this just connect it. A for A, B for line B, and C for line C. Also same. A for A, B for B, and C for C. Okay, now we change the same 0.01, 0.03. Just space it 2 multiply by pi multiply by 50 hertz for the equation inductance, which is J omega L, also like a 2 pi FL. Okay, this is 0.0125, this one 0.025, same. Then change it for RL, the capacitance will disappear. Press OK. Okay, then for this we change, this is bus 1 and the base voltage is 1183 and the swing bus is 0.05, the angle is 0. Okay, here is the bus 2, we change to bus 2. Base voltage is same 11 kV and this is 1, don't change it. Okay, for the this is for bus 3, bus 3 1183, this is 0.4, angle is 0 because we don't have the angle. And now this power guide, first simulation we will choose the phaser. By the way, we cannot change it because automatic solver. So what we're gonna do is go to the gear button, press it. Okay, you can see here solver, simulation time, solver time. Here we choose the ODE 45, which is it can manually lah. Okay, press OK. Okay, you can see here the simulation type can change. Now we will choose the phaser. Frequency we change to 50. Okay, for the tools we will gonna use the load flow. So setting the load flow setting. Okay, max extension we use remove 50, frequency 50. S power, base power is 100 megawatt. This is for PQ tolerance. This don't change. Okay, for the measurement device, okay, what we gonna measure is we have no face to ground, we will face to face and voltage in PU. Current measurement, yes, current PU. Okay, here base voltage is 100 and this 11 kV. The output signal, we will show the magnitude and angle. Okay, same, just follow the previous. Okay, I think this is already finished. So press the button run here, the green color. It show you the result here. We can drag it. So the three upper is for the voltage in PU, and the bottom three is for the angle. This is current. You can see the voltage is same, only the angle because it's three phase. Okay, here you can see it's the stable because this is steady state. Okay, okay, for the load flow analysis, we just click here for guide 2 times, go to the tools and press the load flow. Okay, here you can see the bus 1, bus 2, bus 3. Bus 1 is swing, mean slack, PQ is load, PV is the generator. Okay, here this is V base, U reference angle PQ. Okay, this is from our setting 1.05, 1.04, 400, 250, 200. Okay, just press the compute, and here the calculation. This is 1.05, the angle is 0. For the load 0.9852 and the angle is minus 2.16. For the generator bus 1.04 and the angle minus 0.35. Okay, for the power and the reactive power, this is 214, 149, 400, 250, 200, 130. Okay, we will see the difference and make sure it's right. Okay, here final solution for the V2 as you can see here. So just like this. Okay. V2 means bus number 2. So for bus number 2, you can see here 0.852. This is 0.971. Maybe it's a little different because the iteration, and then this angle just a little different. Okay, this. Okay, for V3 1.04, the angle minus 3. This is a minus 0.4, and then the power we can see at this power flow analysis. Okay, for the bus 1, you can see bus 1 214, 149 for reactive, 218, 140, and then bus 2 is load, is same, and then for the generator 200 and 130. This is 200 and 146. Just a little different because maybe the iteration or they use the decimal point maybe. Okay, this is from me. Thank you.
Okay, and then I will continue to add fault in our circuit. Okay, firstly, click the Simulink link browser and then search for 3, and then we add the 3-phase fault. And then we connect the fault in between the phase bus 3 and bus 2. So connect it. And then double click and enter the initial status is 1 and fault between phase A and ground. And switching times 1/50 and 10 in between 1 to 10. For resistance is 1 exponent negative 10. The snubber resistance is infinity and snubber capacitance is 0. Okay, and then we run the circuit. Based on when we compare the value for the voltage and the current in every bus, we compare it with the normal circuit. For the bus 1, the voltage is 1.05 and the current is 2.26 ampere. But when we add the fault, you can see the voltage is still the same, but the current increase with until 28.79 ampere. For the bus 3 also, the voltage is still the same, but the current is increased like the normal circuit is 2.437, but it at the fault has increased until 44.64 ampere. And for the bus 2, the voltage for the bus 2 is 0.5697. After we add the fault, before we add the fault, the reading is 0.69658. So the voltage is decreased, but the current is also decreased, because at the normal is 4.655 ampere. After we add the fault, the reading becomes smaller. So as for the phasor, the loop flow, after we add the fault, we click the compute, and then you can see the real power and the reactive power after we add the fault. So compare with the normal circuit without the fault, you can see there is 214.85 for the bus 1, 400 for bus 2 and 200 for the bus 3. that for the real power. And we can see for the bus 1, the real power is increased. The real power for the bus 2 is still the same like the bus 3. For the reactive power, before we add the fault, the reading is 149.36 for the bus 1. But after we add the fault, the reading for reactive power is 125.45. So there is decreasing value for the reactive power for the bus 1. For the bus 2, the reactive power is still the same. For the bus 3, the reading are increased. Like for the normal circuit without the fault is 130.61. After we add the fault, the reading becomes 178.16. So that's all from me. And my friend will continue for the other section. Thank you.
Hi, I'm Sabrina. Okay, after fault condition, we're gonna put protection into the circuit. Okay, before we choose to put a circuit at bus bar 2 and bus bar 3. So, before we put the circuit, firstly we delete all this line at bus bar 3 impedance at this transform lines impedance. Okay, and then okay, after that we click Simulink and we choose 3-phase breaker. Okay, for this circuit we use 2 circuit breaker. We use 2 circuit breaker. Okay, and then we connect the line, all the lines, we connect all together to impedance and circuit breaker and impedance to circuit breaker, and then here to here. Connect all this together, and then at fault we connect between impedance and circuit breaker. So we connect here. Okay, after we done connect the circuit breaker into circuit, and then we click run. Okay, from here we can see the difference before we put the protection at fault conditions and after we put the protections. So we can see at bus bar 1 voltage after we put protections at bus bar 1 is 1.05, 1.05 at A, 1.05 at B, and 1.05 at C, and current is 4.917 for A, for B 4.617 for A, 4.617 for B, and 4.617 for C. Okay, and then we can compare, we can see the difference at 4 conditions and voltage, and at 4 condition is 4.105. So we can see that voltage at 4 condition at bus bar 1 is 1.05. For bus bar 2, for B is 1.05, at C 1.05, and current at A is 28.79, at B 2.26, at C 2.26. Okay. After we put protections, the current, the voltage remains same, and the current for A, B, C is 4.617, which is for A decrease, and for B, C increase. Okay, at bus bar bus bar 2, we can see voltage and current at 4 conditions is for A 0.5697, for B 0.9868, and for C 0.5697. And for current at bus bar 2 is 5.725, the power of negative A for A, 4.655 for B, 4.655 for C. And after we put protections, the voltage for bus bar 2 is for A 0.9112, for B 0.9112, and for C is 0.9112, which is we can see the voltage for A and C is increase, and for B is decrease. Okay, at for currents, A is 4.298, and same at B and C, which is we can see at 4 conditions, for A increase, and for B and C also decrease from 4.955 into 4.298. Okay, at bus voltage and current at bus bar 3, we can see at protections condition is 1.04, and same for B and C. And for currents, A 0.3826, and same at B and C. At fall conditions, is voltage is 1.04, same at B and C, which is we can say remain same at fall and after protection conditions. And then for current, this voltage and for current is 4.4 for 4.64 for A, and BC 2.437, which is we can see for A decrease into 0.3826, and for B and C decrease in from 2.437 into 0.3826. Okay, after that we see the load flow of the circuit. Okay, after we compute the circuit, click compute, and okay, we can see the result of the circuit. Okay, for voltage here we can see at 4 conditions we can see it's 0.0500 for bus 1, and this and here for bus 1 after protection is still 0.0500, and for bus 2 for protection conditions is 0.8748, but for under fall condition is 0. Under fall condition is 0.97.1, which is show the decrease before at 4 condition and after we put protections. At bus 3 at protection condition is 1.04, and for 0.04. At 4 condition is 1.04, which is remain same. And for voltage angle, we can see at 4 condition is 0.00 for bus 1, and For protection condition, it still remains same 0.00. And for bus bar 2 at 4 condition is negative 3.78 at 4 conditions, and at protection conditions for bus bar 2 is negative 5.68, which is increase. And for bus bar 3, voltage angle is 3.05 for protection conditions, and for fault condition is negative 1.31, which is show decrease. Okay, for reactive power, for bus bar 1 at protections conditions is 251.92, while at for conditions for bus 1 is 366.27 for reactive power bus 1, and reactive power for bus 2 is 400 for at protection conditions, and for condition at bus bar 2 still remains same 400, and for bus bar 3 at protection condition is 200, and at for conditions the reactive condition the reactive powers remains same still 200, and for this and for Q for bus bar 1 at protection conditions is 460.07, and at for conditions is 125.45, which is show the increase after we put protections into the circuit. And for bus bar 2 is for protection condition is 250, and at for conditions still remain same 250.00, and for bus bar 3 at protection conditions negative 102.39, and at for condition is 178.16, which is show decrease. Okay, that's all for me. Thank you.
Question part, software that we use is MATLAB. And why we use that? Because in our book that we use as a reference, Hadi use this simulation. And the second is to enhance the ability and capability for the student to simulate the circuit. And advantage of using it because it compare more detail, it compare the result in detail, such display the load flow analysis. And the second, it's suitable for engineering simulation. For the limitation is too complex in component. And the second is slow in software usage, such that when we use the software, we assemble the component, it will burden the computer because we use too many components to simulate it. And the fifth, what makes a good protection system is calm in preparation of fault system protection. Okay, that's it.
In conclusion, this project allows us to understand power system element behavior in different condition and respective protection. Thank you.